Hasanat just said is true, right? So it is certainly the case that, as Hasanat said, EQL returns T when you compare a symbol to the same symbol, right? So you're not missing anything. What you said is perfectly correct. All right. EQL is the standard comparison predicate in Common Lisp. So there are some built-in functions, and one that we will see later today is member, and at a later point this semester we'll look at a SOC, that have to do some comparison to work. So member tests whether its first argument belongs to the list that is given by the second argument. So it has to test whether its first argument is equal, in quotes, to different elements of the list. Now, once it finds, so let's say that the first argument is 5, and the list is 1, 5, 7, 4, right, a list of 4, then 5 is not equal to 1, but 5 is equal to 5, and so then you can stop, and member can say yes, or T, because 5 is a member of 1, 5, 7, 4, okay? But what equality test is used to do the comparison? And the answer is, by default, EQL is used. It's the standard comparison predicate. If you want a different predicate to be used, like equal, then you have to tell the function to use that predicate. If you don't say anything, if you just call member, then the predicate that will be used is EQL. All right, so that's something to remember. Right now, this is a page that you'll need to read if you haven't read it already before Wednesday's class. It's one of the it's a part of reading assignment day. Okay, so be sure to read this page after class for yourself if you haven't read this already. Now, in the scheme dialect of this, we have analogues of equal, EQL, and EQ, but they have slightly different names. So the analog of equal is equal question mark. The analog of EQL is EQV question mark. And the analog of EQ is EQ question mark. However, a member and ASOC don't use EQV as the default equality test. They actually use equal. So that's the difference between scheme and Common Lisp. Now here is a fourth equality predicate. And this equality predicate differs from the other three in a number of ways. In 3 ways, actually. So 2 of them are actually shown here. So the first way is actually very obvious from what you see here. So this equality predicate can take more than 2 arguments. It can take any number of arguments. So if you use equal with more than 2 arguments, you're going to get an error, right? It doesn't work. That's too many arguments, right? So the EQL, too many arguments, right? So you can't, it doesn't return T or nil. It just says error, too many arguments. But you can use equals with any number of arguments. So this will just give T. And you can have more than 2. So 4, 3. So now we've got 5 arguments. And that will give nil, actually, because this 4 is not equal to 3. So therefore, you can get nil, right? So again, you can't use any of the other equality predicates because there are too many arguments. So that's the first difference. The second difference is that if any argument is not a number, then what will happen is that this equality test will produce an error. All right. So if we take a look here, right? So equal 1, 1, right? So that is fine. That's not going to produce an error. If we just say no, they're not equal, you get nil, right? But if I try that with this equality predicate, it's not going to give T or nil. It's going to give an error, right? 1 is not a number, right? Because this argument, the arguments must be numbers, right? If any argument is not a number, right, you're going to get an error, right? So what that means is, if you know the arguments are numbers, then there's an advantage to using this equality predicate rather than one of the others, right? Like equal or EQL. The reason is many bugs in computer programs are caused by the programmer knowing something is true when in fact it's false, right? So you know something, you know a certain fact, but it's not a fact. It actually isn't even true. And now, so let's suppose you know, in quotes, that the arguments are numbers. Then if you're actually wrong, and one of the arguments is not a number, you'll find out straight away if you use this. Whereas if you use equal, you wouldn't find out straight away. Now, as a general rule, you want to find out there's a mistake as soon as possible, right? That makes it, the longer it takes for you to find out that something is wrong, in general, the harder it is to, the more work it takes to fix the problem, and the more trouble can result from your bug. So a good thing about using this is that if any argument is not a number, it will give you an error, right? Whereas using equal, the other one doesn't have that advantage because, you know, you just one, right? The problem with this is it doesn't give you an error, right? So if the arguments were supposed to be numbers, then your code will continue to execute very happily, and you will never find out that your arguments are not what you think they are supposed to be. All right. Now, if the argument values are all rational or all floating point, then the predicate returns t if the argument values are all equal, and returns nil if at least one of them is not equal to one of the others, if there are at least two arguments that are different. Now, what happens if there are both rational and floating point argument values? Now, you'll remember from the discussion of equal and EQL that you get nil, right? So equal to 2.0, right? That gives nil, right? Because one of the arguments is integer, one of the arguments is floating point, right? Nil. But if you use this equality predicate, you're going to get p, all right? The reason is that this equality predicate converts. So if you have both rational and floating point arguments, then any floating point arguments will be converted to rational before comparison is done. So if there are both rational floating point argument values, floating point values are coerced to rational before being compared to rational values. Now, this can always be done without error, right? So any floating point value is equivalent to a rational value, is exactly equivalent to a rational value, right? This is like when you probably learned in elementary school that the decimal number can also be written as a fraction, right? So 1, 2, or have you got this decimal number? That could be written as 17341 divided by 100,000, right? So any decimal number can be written as a fraction. And similarly, if you have a binary floating point number, like that, that can be written as a ratio, right? That would be 1011101011, right? Base 2. Right, divided by, if I turn off this, what happens if I turn on this light? Does that help? No, that doesn't help. Maybe that's a little bit better. All right, so divided by 100000000000 base 2, right? So that would be 2 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2 to the 10, 1024 in the denominator, right? So any floating point number is equivalent, is exactly equivalent. For any floating point value, there's a rational value that is exactly, that's mathematically equivalent to it. Now, the converse is not true, right? You can easily write ratios that aren't equivalent to any floating point value because floating point values are stored with a finite number of bits of precision. So for single precision for a floating point, called single float in this and called float in C++ or Java, you only have 24 bits of precision. And for double precision floats, or double float in this, and double in C++ or Java, you have 53 bits of precision. But still, the number of bits is finite. And so you can easily write down ratios that can't be represented using a finite number of bits, because then you get a recurring bit pattern, right? So in fact, any ratio which when expressed in lowest terms has a denominator that's not a power of 2, will not be expressible using a finite number of bits. All right, so any floating point value is mathematically equal to some ratio, but most ratios actually aren't mathematically equal to a floating point value, because you've only got a finite amount of precision in the floating point value. But anyway, what this is saying is if there are both rational and floating point arguments, then the floating point values are converted to rational, and then you do the comparison. So for example, this 0.5 will be converted to 1/2, and then you compare those two, and so you get t, right? Now this one would give nil, because this side is floating point, and this side is a ratio. Now, one thing to be aware of with floating point computation is that rounding error happens very frequently. And because of rounding error, when you test floating point values for equality, you end up getting a result of nil or false, even if when in the absence of rounding error, you would get t, right? So this is something to be aware of. So testing floating point values for equality is dangerous. It leads to it will easily produce bugs, because two things that seem as though they might be equal may actually not be equal because of rounding error. So let me give an example of this. So floats are stored to a precision of 24 significant bits. So in binary, suppose we look at the number 0.2, which is 2/10. Now, that simplifies to 1/5. 5 is not a power of 2. So if you try and represent that in binary, you will get a recurring bit pattern, right? Like this, they go 1, 1, 0, 0, repeating again and again forever. Now, since a float only has 24 bits of precision, you can only store that number of bits, right? So the closest you can get to the actual value is this, right? Where you round the 0 to 1, all right? The floating point value 0.2 is actually represented by this, which is actually slightly bigger than 0.2, all right? So the float 0.2 slightly exceeds a fifth, and therefore equals 0.215 is actually going to give you nil. So in fact, let's make sure this is clear. So let's convert 0.2 to a rational. Right, so that is the value. Let's write that out in binary so you can actually see what that value looks like, what the bit pattern would be. So let's use the format function, format nil, and let's format it as a binary. So we're going to we're writing this ratio out in binary rather than decimal notation. So you see this, it's actually this, right? So you see that this 1 at the end. So what I've highlighted here is exactly the number that I put here. Like that, with a 1 at the end. Right. So 1/5 is actually equal to this number, right? So 134217773 divided by 67108864. Right? So those two are equal. What? 134217773 6710. Oh no! Oh no, not equal to 1/5. Right? I'm mixing my 1/5. Obviously, is equal to that. What I meant is 0.2 is equal to that, right? All right. So those two are equal, right? So 1/5 obviously isn't equal to that. That was the whole point of this discussion, right? So there's some rounding. 1/5 is 1/5 is this one going on forever, right? And this other thing over here is this thing down here, the rounded value, right? So 0.2 is equal to this thing, all right, which is not a fifth, right? So in fact, if you multiply the numerator by 5, you don't get the denominator, right? You get something that's slightly bigger than the denominator, right? You get something that's almost the same, but with a 5 here, okay? So therefore, so this, I hope makes clear what's going on here, right? So 0.2 slightly exceeds a fifth, and so equals 0.2 a fifth is nil, And the reason 0.2 slightly exceeds the ratio 1/5 is because of rounding error. Now, another example might help, but let's use an example. Suppose you're visiting a planet where people have 3 fingers instead of 10. Then those people would write in base 3. So if they wanted to write 2/3, those people would write 0.2, right? So because they're using base 3, for the people on this other planet who have only 3 fingers, that number is 2/3. Right. Now, let's suppose these people use computers that work in decimal rather than binary. So exactly how would they represent 2/3 in their decimal computer? Well, in a decimal computer, you would have to have 2/3 looks like this, with 6 is recurring. But let's suppose that their computers only allow 6 bits of precision. Then you can't have all these other 6s. So what they would actually have is 0.6666667, right? Like that, right? So they would represent. So for them, you see, if you use a decimal computer, this would be represented like this, right? And this number is slightly bigger than 2/3. So that's exactly the same principle. Okay. So, but there's a bigger point here, which is that testing floating point values for equality can easily lead to bugs because of rounding error, because you forgot about rounding error. And what sometimes makes these errors worse is that they're not portable errors. Sometimes 2 things test equal, but then when you change the optimization level, then the code that's executed is different. And as a result of that, the rounding error is not the same as before. And so a program that behaved one way may actually behave a different way when you change the optimization if you're testing floating point values for equality, right? So if you had some condition like if let's write in Java syntax, if x is a floating point value and your test x equals to y, so that might return true, but when you change the optimization level of your compiler, or if you use a different compiler, then this same test might return false. And we're talking about the same program that you're compiling. And so that's why these kinds of bugs can be especially problematic. That's one reason. Okay. So testing, the best thing to do is to avoid testing floating point values for equality. Right. Every time you see a test of 2 floating point values, testing where 2 floating point values are equal, just bear in mind that that's a dangerous thing you're doing, and the code may well not behave the way you expect because of rounding error. Right? So that's something to remember when programming. All right. Now, frequently used predicates. So not x and null x are mean the same thing as EQX nil. All right. So not and null are completely equivalent to Lisp, but they're completely equivalent in Lisp, but they're used differently. So not is used to negate a Boolean value, and null is used to test whether an argument is the empty list. Right? So not x is used to negate a Boolean expression, as in this green expression. So here we're going to negate the Boolean value equal x dog. Right? So x is not equal to dog, then something. Null x is used to test whether the argument value is an empty list. So is 17 an empty list? No, right? So you get nil. Now, what about the CUDA of the list 17? So that means the list you get by removing 17 from this list of length 1. So the CUDA of this list is obviously the empty list. So that's why you get T. And actually, this null CUDA is a very good way to test whether the list L has length most 1. So this is going to return T if L is a list of length at most 1. If L is already nil, then the CUDA of nil is nil, right? That's why the null of CUDA L returns nil if L has length 0. But if L has length 1, then returns T rather. So if L has length 1, then null CUDA L again returns T. So null CUDA L returns T if the value of L is a proper list of length at most 1. And null CUDA L returns nil if L is a list of length at least 2. So here is Turetsky's description of null and not. So Null behaves just like not, right? Returns T if its input is nil. But they're used differently. Right? And this programmers use not for logical operations, changing true to false and false to true, as in this example. They use null when they want to test whether a list is empty. There's a variant of null called NP that produces an evaluation error if the argument value is not a list. So if the value of x is a list, then NPX has the same value as null x. But if the value of x is not a list, then if you try and evaluate NPX, you're going to get an error. Okay, so if you try and evaluate NP7 or NP quote A, you'll get an error. So NP 0.7. You're not going to get T, you're not going to get nil, you get an error. Right? Now, null 0.7 is fine, right? You'll just get nil because 0.7 is not the empty list. So just as I mentioned a moment ago, that an advantage of this predicate over EQUAL is that if you know the arguments are numbers, using this has the advantage that if you're wrong and an argument is not a number, then you'll get an error, right? So similarly, if you know the argument is a list, then using NP has the advantage that if you're wrong and the argument is not a list, you find out immediately. You get an error. Now, a list is dynamically typed. So what that means is the type of an expression is not known in advance in general. You have to wait till you evaluate the expression to know. And sometimes, depending on what type the expression has, you want to do different things. So it's very useful in Lisp to have some way to determine the type of a particular value. And type P is a good way to do that. So type P x quote type returns T if the value of x is a value of the type whose name is this thing. And it returns nil if the value of x is a value that's not of that type. Now, what type names can we use? The answer is all the names in this tree from figure 12.1 to Aretsky, except for common. Common is now obsolete anyway. Now, this tree actually is not quite exactly the same. It's not exactly the same as the tree in Aretsky because I add atom and real. Because I added two other types, so you can actually use atom and real as well, but Turetsky doesn't mention those. So this is from section 12.2 of Turetsky, also the section that introduces type P. Unfortunately, in the old edition, figure 12.1 is missing. Right, so if you look at section 12.2, you see for some reason Turetsky didn't include the figure. Maybe he wanted people to buy his later edition. Right? Anyway, if you're using the free edition, well, then you can have a copy of that picture on here. You can actually access a copy of the 2013 edition from the library. So Queen's College students have access to a copy, an online copy of the 2013 edition. So if you look at the first page of the first day announcements, you'll see how to access that library copy. But anyway, so type P3 number, you'll get T, right? 3 is a number. Type P3 integer, you'll get T. 3 is an integer. Type P3 float, you get nil because 3 is not a type float. Type P foo, quote symbol, you get T because foo is a symbol. So T, T, nil, T. And so Turetsky says T appears right at the top. So everything is considered to be of type T. Okay. And I deleted the common sentence because that doesn't, common is now obsolete. It's not, so you shouldn't be using common. Now, null is the type whose only member is the empty list. The list type comprises null, which means the empty list, and cons, which means non-empty list. Okay? So a list can either be a non-empty list, it's called a cons, or it can be an empty list, which would have type null. And nil is a symbol as well as a list, so that's why the null type is a subtype of the symbol type. Okay. And we have the real type, which includes all numbers other than complex numbers, and complex numbers are numbers with a non-zero imaginary part. You won't have to use complex numbers. And atom is the type that comprises all values that are not non-empty lists. So a cons, in other words, a non-empty list, is not any other value is an atom. So the 11 box types are the type names you have to know about for this course, right? So repeated them here. We'll also use strings, but only as follows. The 11 box types are the types you have to remember. For 8 of the 11 box types, that means all of them except for atom, null, and ratio, you, instead of writing type px quote type, you can just write type px like this. For example, you can write integer px instead of type px quote integer. So that's something to remember. So here are some examples that you should have seen already. Page 8 of Turetsky number p, right? That tests whether the argument is a number. Symbol p, testing whether the argument is a symbol. List p, testing whether the argument is a list. So all of these are examples. Cons p is testing whether the argument is a non-empty list. Okay, so the cons p of nil returns nil, whereas this p of nil returns t, right? Because the empty list is not a cons. So cons px returns t if the value of x is a non-empty list, and it returns nil otherwise. In other words, the value of x is an atom. So atom is the opposite of cons p. Right? So here are some simple examples of atom. Right? And let me just remind you that the built-in function names atom and null do not end with p. So it's atom x, not atom p. Null x, null p. Right? That's just a reminder. And now we've got some predicates for testing greater than and less than or equal to, greater than or equal to, less than or equal to. So they work like equals. So just a quick bit, there's nothing surprising here. If there are both rational and floating point arguments, the floating point values are coerced to rational before comparison is done. So this gives you t, because 0.5 gets coerced to 1/2. All right, so greater than or equal to, less than, and less than or equal to work just like greater than or analogously. And again, you've got to be careful because of rounding error. So this returns a t because 0.2 actually slightly exceeds a fifth, as I showed you earlier. We've also got 0p, even p, odd p plus p minus p are not equal to, right? 0p is testing whether x is 0. Even p and odd p are testing whether the argument is even or odd. Don't use even p and odd p with arguments that are not integers because you'll get an error. Plus p is testing whether the argument is positive. Minus p is testing whether it's negative. And this is how you test whether two things are not equal, right? You can also use a slash equal with more than 2 arguments, but it's not done very often. So usually you just use not equal to with 2 arguments. Now there's member. So it's used to test whether an argument is a member of a list. Actually, I'm out of time. Maybe we'll just stop there. I'll just post a few more, but I think I'll go over these slides at the beginning of our class next time. Right? This is where I got to in the 5 o'clock class. I think we'll begin on Wednesday with a discussion of member, but I'll just post this anyway so that people can read ahead. Okay. And part of reading assignment A that you're asked to do before Wednesday discusses member. Okay. So by Wednesday, you should have done reading assignment A, and so you should know all this already anyway. All right. So I think since we're out of time, I think we better stop. So does anyone have any questions at this time? Let me turn off the recording, and then maybe someone will think of a question. Stop recording. Okay, so now the recording has stopped. Does anyone have any questions this time? Can I repeat what NP does? Certainly. Okay, so NP behaves like null, but it gives you an error if the argument is not a list. So let's just go back to the discussion of NP. So NP, if x, the value of x is a list, okay, then NPX is the same as null x. But if the value of x is not a list, then if you evaluate NPX, you get an error, right? So you do NP of anything that's a list, right? Then that's fine. That will return null because a nil, rather, because that's not the empty list, right? So you get nil, right? So that's exactly the same as calling null. But if you have something that's not a list, right, like 67, null will return nil because 67 is not the empty list. But NP will do something different. It will give you an error, right? Because the argument is not a list, right? You get an error. So that is the difference between null and NP. Are there any other questions?
So if you did 67 in parentheses, it would give you nil?
That's right, exactly.
Okay.
Good. So what I'm being asked is, suppose I did that, right? So is this the empty list? No, it's not, because it's got 67 in it, right? So you get nil. So in that case, it's exactly the same as null. What can be used instead of, you should never use setf when writing your own functions. So what would you use setf for, right? You would use setf to change the value of a variable, which you're not allowed to do. So if you ever try and give a value to a variable using setf, then you must not, so you would get 0, right? So never write functions using setf. Setf is only for testing your functions. So never, if you look at the solutions to assignment 2, you will see I never use setf in any of those functions, right? If you look at all the functions I've given earlier, you will see that we never use, I define factorial, obviously I didn't use setf, because once you use setf, you're giving a value to a variable, and that variable can be used later. So you have a side effect, and that's not allowed in functional programming. So you must not give a value to a variable in functional programming. So never use setf when writing your own functions. Okay, so look at the examples of functions that are in solutions to assignment 2, and also in the examples we've done so far in for function definitions. If so, that may help you and anyone else get a clearer understanding of what of how you should write functions. So we can't have a temporary variable. Now, it depends on what you mean by temporary variable. I mean, you can have local variables, but the local variables are actually local to the function. And we haven't talked about local variables yet. But later on, after we talked about predicates, I will introduce the let form. And the let form and the related let star form are used to introduce local variables. The difference between let and let star on the one hand and setf on the other hand is that setf gives a value to a variable that can be used outside the function. So that's why setf is considered to be to have a side effect. Because if your function uses setf, then when the function returns control to its caller, that variable still has a value. And so calling the function had a side effect. Whereas if you use let to create a local variable inside your function, then when the function returns, the local variable has disappeared. So using a let or let star does not make your function have a side effect, because the local variable is completely local to your function. Okay, so let and let star can be used to create local variables, and I will spend some time talking about let and let star later. But right now, for assignment 3, nobody should be using let and let star, because that's something that will be dealt with at a later time. Okay, so can I come to, yes, if you, I have an office hour period right now, so if you would like to see me, Shay, certainly you can do that right now. Are there any other questions this time? So Shay, you know how to go to the Zoom room, right? I'm assuming you know how to go to the Zoom room to the course. Yes, okay. So I'll see you there as soon as I sign off from this class. So assuming there are no other questions, I'm going to sign off now. So I look forward to seeing you all on Wednesday. Please try and do reading assignment A from last Friday's email before Wednesday's class. So good night, everyone.